In this video, we are going to study concept of convolution integral. To understand this concept, we need to consider an LTI system. Here, this LTI system means our system is linear and time invariant system. Now, why we need to assume it, we will see it in the coming explanation. So, as we know, the system is represented in a simple block with its transfer function h. This system is applied with certain input and it generates certain output. So, towards left hand side we have inputs and towards right hand side we have the outputs. Now, in case of convolution integral, we are assuming this system to be a LTI system. Therefore, if I consider, I am applying impulse function to the system, which is delta t. And if we go through the concept of impulse response, the output which I get for this system will be h of t, which is called as the impulse response. Now, as our system is linear, we can change the input. Therefore, if I apply delta of t minus some constant, let's say tau, at the input, I am going to get the desired output as h of t minus 2. It is because of the property of linearity. Secondly, our system is time invariant system. In short, we write it as TIV, TIV, time invariant system. Now, what this time invariance states that if I scale my input by certain factor, let's say a into delta of t, I will get output as a into h of t. Similarly, if I apply delta 1 of t as input, I will be getting h1 of t as output. If I apply delta 2 at input, I will get h2 of t at output. And now, if I apply both the signals simultaneously as delta 1 of t plus delta 2 of t, I should get the output of system as h1 of t plus h2 of t. It is because of the property of time invariance. Now there is one more thing, that if I apply all these operations together, mean if I scale delta 1 by, let's say, factor a and delta 2 by factor b, I should get the same scaling of a and b in the output. So this is because of the time invariance property of the system. Just remember the final equation, which is scaled version of impulse function added with another scaled version of the impulse function, and the output is scaled by same factor with the impulse response and the same scaling factor for the second part, which is h2. So here this equation is very important. Based on this, we are going to see the concept of convolution integral. Now let us see the concept of convolution integral. A simple system is represented over here. This system is applied with the input as delta t and we are getting the output as h of t. So this output is called as impulse response, as this system has the input applied as impulse function. The input-output relationship of this system is denoted as output h of t is operated by the system transfer function and the input is the impulse function. Now this becomes the known things for us. Means if I have a system whose impulse response is known, system with impulse response h of t is known. Now I need to apply x of t to the system and I need to find out what will be the corresponding output for this system. Now, the aim in convolution integral is I need to represent this given signal x of t in terms of weighted function of impulse function. So weighted function can be like a into delta function, weighted impulse function, as well as time shifted version. So delta of t minus 2. So if I have such kind of input and my system is LTI system, for this corresponding equation, output of my system will be a into h of t minus 2. Now this x of t signal, this entire signal, I want to represent in terms of this impulse function. So when I represent this x of t in terms of impulse function, I'll be applying the rule of impulse response to obtain my output. Now consider this x of t signal as shown in this diagram. Now I need to mark a single point on this signal. So let's say at time equal to 2, the amplitude of signal is A. So I need to represent this amplitude A. This amplitude A can be represented as x of tau. So this is value of or the amplitude of signal at time equal to 2. My next aim is that I should represent this single point, which is of x of t, in terms of impulse function. Therefore, so first recall the concept of impulse signal. So impulse signal is simply a signal with amplitude 1 at origin. So if I say this is time axis, this is a delta t axis, my impulse function is having amplitude 1 at origin. So this is what a simple signal represented at origin. Now if I multiply this impulse function with the given x of t signal, there won't be any change because the amplitude of impulse function is 1. But I need to change the position of this impulse function. So instead of this impulse function occurrence which is at origin, I need to shift it further at time equal to 2. Therefore, this signal will be converted into a new function which will be the shifted version of my impulse function. It will be delta of, here I need to shift this signal at 2. So my impulse function will have amplitude 1 at time equal to 2. Therefore, this shift is towards right hand side. Therefore, I need to subtract that respective shift from the t function. So it will be x of t minus 2. Now if we consider this a point, this a point is nothing but amplitude of signal at single point. So it is as good as a constant value. Now this a can be represented as c x of tau multiplied by delta of t minus tau function. Here this x of tau will be the corresponding amplitude of x signal at time equal to tau, and this impulse function which is shifted at tau will have amplitude equal to 1. So this equation will not have any change in the value which is amplitude a. So this we have represented a single point on this x of t signal in terms of impulse function. Here x of t will be acting as in weight of this function, and impulse, this is time shifted impulse. Now our aim is to represent this entire x of t, all the points on this x of t signal, all such points on this x of t signal in the same equation of what we have derived now, a equal to x of tau into delta of t minus 2. Now to represent all the points, our aim is just to change the value of tau. So if I want to find out, or I need to represent x of t signal at time equal to 1, the value of tau will be 1. Therefore this impulse function will be shifted at t minus 1. Similarly, if I need to represent x of t signal at t equal to 2, I need to change the value of tau equal to 2. Therefore, I need to accumulate all the values of tau in this equation. To accumulate all the values and get x of t signal, we need to integrate the above equation. So it will be integration x of tau into delta of t minus tau d2. This integration is function of tau, and this tau will vary from minus infinity to plus infinity, so that it will collect all the points on x of t signal. So with this equation, we have the input signal x of t. It is represented in terms of weighted, so this is the weight, time shifted impulse, this is time shifted impulse. So all the points on x of t are now part of impulse function. Now our next aim is to find out the output if I apply x of t to the given system. Now for this given system, input applied will be x of t and output will be y of t. So as we know the concept of impulse response, which is denoted as transfer function operating on the input delta t. So same concept is applied over here, and now our output y of t will be equal to transfer function operating on the input x of t signal. Now we have the representation of x of t in terms of impulse. So h operating on x of t is given as integration minus infinity to plus infinity x of tau h of, sorry, it is not h, it is delta of t minus tau d tau. It is the generalized input output relationship for any system. Now if you look at this equation carefully, x of tau is a simple constant, h is the transfer function, and delta is the impulse function. So this transfer function will operate on the impulse function, and this equation will become now integration minus infinity to plus infinity, x of tau will be as it is, and this h is operating on the impulse function d2. Now as our given system is LTI system, this equation delta of t minus tau is nothing but it is shifted version of impulse response. So this y of t, we are going to get the final equation as integration minus infinity to plus infinity x of tau into output, because of the impulse delta t minus tau will be h t minus tau d tau. So this equation represents convolution integral. The meaning of this equation is I can find out output for an LTI system provided I know the response, impulse response of the system for any input signal x of t. So if you represent it in more appropriate way, it is like y of t is obtained from input signal x of t by convolving this x of t signal. This asterisk symbol represents the convolution. So convolving the input x of t signal with the given impulse response of the system. So if we convolve input signal with impulse response, we are going to get the desired output. So this is the representation of convolution integral. On the same grounds, we can now derive the equation for convolution sum. So I'll be directly stating the equation now. So for convolution sum, it is discrete signal. So output y of n will be equal to, integration will be replaced by summation k equal to minus infinity to plus infinity, input x of k into the shifted impulse response h of n minus k. On the same ground, this y of n can be represented as x of k convolving with h of, now instead of k, now here it is, we have written it as in terms of n. So x of n convolving with h of n. So these are the concepts of convolution sum and convolution integral.